Welcome to Chapter 7 of Class 9 Science, Motion. In this exciting chapter, we'll explore how objects move and how we can describe their motion mathematically. We'll learn about distance and displacement, speed and velocity, different types of motion, acceleration, graphical representation of motion, and circular motion. Get ready to understand the mathematical language that describes everything from a walking person to orbiting planets. Let's begin by understanding how we describe motion. The first step is describing position, but position is always relative to a reference point. This explains why passengers in a moving bus see trees moving backward. They're using the bus as their reference frame. We also need to distinguish between distance, which is the total path length covered, and displacement, which is the straight line distance from start to finish with direction. This distinction is crucial for understanding motion completely. Now let's explore speed and velocity, the measures of how fast objects move. Speed tells us how fast, while velocity tells us how fast and in what direction. We calculate average speed as total distance divided by total time. The walking speed activity helps us understand these concepts practically. Remember that an object can have speed but zero velocity if it returns to its starting point, like Usha swimming back and forth in a pool. Let's examine different types of motion. In uniform motion, objects cover equal distances in equal time intervals, like a car on cruise control. In non-uniform motion, objects cover unequal distances in equal time intervals, like a car in city traffic. Distance-time graphs help us visualize these motions: straight lines for uniform motion and curved lines for non-uniform motion. Most real-world motions are non-uniform, but studying uniform motion gives us the basic framework. Now let's discover acceleration, the rate of change of velocity. Acceleration makes motion exciting. It can be positive when speeding up, negative when slowing down, or zero when moving at constant velocity. The toy car experiment demonstrates acceleration practically. Velocity time graphs are particularly useful for understanding acceleration. The slope gives us acceleration, and the area under the graph gives us displacement. Let's explore graphical representation of motion, turning motion into visual pictures. Distance-time graphs show how position changes with time, with slope representing speed. Velocity time graphs show how velocity changes with time, with slope representing acceleration and area representing displacement. Acceleration time graphs show how acceleration changes with time. These graphs transform complex motion problems into simple geometric calculations that reveal patterns in motion. Now let's examine circular motion, motion along a circular path. This includes everything from merry-go-rounds to planets orbiting stars. In circular motion, even when speed is constant, velocity keeps changing direction, which requires centripetal acceleration directed toward the center. We calculate centripetal acceleration as versus squared divided by r. This acceleration is what keeps objects moving in circles rather than flying off in straight lines. As we conclude this chapter, let's review the key concepts and their practical applications. We've learned to describe motion mathematically, distinguish between different types of motion, calculate speed, velocity and acceleration, interpret motion graphs, and understand circular motion. These concepts help us analyze everything from vehicle motion to planetary orbits to sports dynamics. Motion physics forms the foundation for understanding more advanced topics like forces, energy, and the fundamental laws that govern our universe.